turbulence modeling class, and it was earlier asked what happens when compressibility effects occur, and I had one answer was that usually these models are developed in an incompressible framework and to make compressibility corrections. Probably the more proper way to do things is to do some averaging or techniques on the actual full equations where that assumption is not made. And so today we're going to look at the incompressible formulation, remind you about that, and then introduce what's called mass averaging. And that's where we'll obtain the full set of equations. And it does cause some dilemmas. So some CFD codes will use these types of equations, and some will use incompressible ones where they make compressibility corrections. So we're going to look at that today and what those equations really mean. All right, so from the handout I gave you, you can see this. And this is really the only figure for this class, and maybe part of the next one, depending on how far we get, is this screenshot by AJ Favre. And I'm horrible at French names, so I actually looked that up before coming. And I think you're a native or fluent in French, so how's my pronunciation?
That's good.
It's pretty good, Favre. Okay. And anyway, it's maybe like this. Something like that. But this is a famous paper. I put it up on our class website. And so this is, the notes I have are kind of developed from separate sources, kind of a Frankenstein class. But this is one great source where it's a report. Obviously, it's down here in the Institute of Mechanics and Statistics of Turbulence, right here. And he was actually funded by, I believe, a DoD grant from the United States. So you know you're good if you're in France and you're getting American DoD money. That probably means something. Anyway, let's look at what we have here today. See them right there. And you might recognize this equation, right? This is, again, the continuity equation, right? So that's conservation of mass, momentum, energy, and these are exactly the same equations we introduced earlier. And they're compressible because, of course, they have densities in the time derivatives and equations, and they're not brought outside other spatial derivatives like here. So this is definitely a full set of equations of continuity, mass, momentum, and energy. So in these notes, this should look very familiar to you. I'll just remind you what the variables are. Maybe not everybody's seen these full forms before. Stress tensor, tau ij, and you see here's the first coefficient of viscosity, mu. So that's the one we normally talk about. And then there's lambda. That's actually the second coefficient of viscosity, and it's usually approximated using Stokes' hypothesis that it's negative 2/3 of the first coefficient. So you can define it that way. See, it's right here. Mu is the bulk or second coefficient of viscosity. It's negative 2/3 mu. So we would separate or put that back in the equations. This is basically a Fourier law for heat conduction, where K is a heat coefficient, conduction coefficient. T is temperature, H is total enthalpy, little h is static enthalpy, and of course total enthalpy is static enthalpy plus the trace of velocities, which is the kinetic energy. So we'll have this energy equation right here for total energy, and we have one for static enthalpy. So we just take this form, 2.6, substitute it in 2.3. What do we get? We get a static enthalpy equation. So sometimes, and hey, well, there's a sheet there, AJ. Sometimes it's more beneficial to solve one or the other, or even simplify it further for like temperature or pressure if you make certain assumptions like calically perfect gas, or substitute it for an entropy equation. Once again, remember, delta ij is Kronecker delta function, which is used in these equations, and it's a value of 1 for I equals j and 0 otherwise. And remember, we're using Einstein or index notation. If you're seeing summations I and j's, you sum the terms, right? So this is all kind of things we've already talked about, but it's good to kind of mention it again. With that assumption here, or not assumption, excuse me, definition, you can find 2.7 for a conservation equation for energy in terms of static enthalpy, little h. Okay. It should be noted that all these equations, remember, as they're written, can be used for laminar or turbulent flow, transitional. They're just the general equations, and there's no solution. Once again, we might replace the values with averages and fluctuations. And that's what was originally done by, of course, Reynolds and his contemporaries. And of course, a approach might just be to directly solve these with closure and modeling, which we'll get more details later in the class. And you probably looked at the previous set of equations and said, wow, we made an incompressible assumption, and the equations are huge. And if we didn't make the incompressible assumption, we did Rand's modeling, there's even more terms that we would need to model. And so Favre, he really came along and said, I'm going to do mass averaging to try and reduce the number of terms and get them to be as close as possible as the original Rand's equations. And that was a huge breakthrough, and why so many people talk about the Favre-Averaged equations, which we'll write as FANS sometimes, Favre-Averaged Navier-Stokes. And that's one thing we'll look at, and we'll look at how these averages are done in a second. So it's usual in these approaches to average over the whole equation. Okay? And you can do that by two ways: the conventional averaging, which is Reynolds, or Favre. So those are the two ways to do it: Reynolds averaging and Favre averaging. So we want to do this for the flows. We have basically three major equations. One's a vector equation, and you know it's very conventional and convenient to replace the instantaneous quantities by their mean and fluctuating quantities. So here is our traditional averaging approaches. Right there. And in this case, you'll note that we are using a double prime in the notation of Favre. So that's your time average plus your fluctuation. And just to remind you of some of the rules for how long these averages might take to get statistically independent solutions for the averages, you might say, well, typical average time is on the order of minutes, for a typical one-tunnel test. And it would be only useful if your averages are really independent of the time t. And that just means you have a statistically stationary flow. For these cases, and remember the fluctuations are not too large. Ensemble averaging can also be used. And there's a whole discussion of when these things are applicable and not, and I think that reference, according to my notes, is in Bradshaw in Journal of Fluid Mechanics in 1971. And I don't post that article on our class discussion website, but you're welcome to look it up. Okay. Now we might say, well, once again, there's that definition, and this is the same one as before. We would be the limit of delta t going to infinity of what? An integral from, say, t naught to t naught plus delta t of q double prime of t dt. And of course, if we are averaging the traditional fluctuation, that would be 0, right? So that's pretty straightforward. So that's the limit of delta t going to infinity from t naught to t naught plus delta t of q double prime t dt is 0. And I apologize again for my writing. That's why I'm not in art or calligraphy. So we can apply this simple definition once again to Q, and this is what we've done traditionally. We'll have a term for density, where x is your spatial position from I equals 1 to 3, and t is time. And then we have our barred quantities, which is our traditional average defined here, plus the fluctuating, which is double prime. And that's exactly the same thing for all the other variables, velocities too, of static enthalpy, total enthalpy, and temperature. And just like in 210, if we're doing averages of all the fluctuating parts, the bars of the double primes, those go to 0, right? And we looked at those graphs previously. But now we're going to do this averaging on the compressible equations. And this is where we're really diverging from our previous ideas. So if we take these expressions, 2.8, well, it's really 211, yeah, maybe 210 through 2.14, and we put into equations 2.1 and 2.2 in this set of notes, what's going to happen? After we simplify a bit, we'll get a Reynolds averaged compressible form, right? Which should reduce the incompressible form if we make the incompressible assumption, if we've done everything right. And that's what we got here. We got continuity and a momentum term, right? And let's just look at these for a second. They're immensely huge. So here's the conservation of mass equation. And without that partial rho bar partial t term, we have an extra term here in the second term, rho double prime, u double prime bar. And unlike just the incompressible rands, that didn't exist. So there's another term that we get right when we average the compressible equations, which makes life really difficult, because we don't have a transport equation for that. Now let's look at momentum. We also have rho prime prime, u prime prime bar. We have an energy term. The pressure gradient is fine, that wasn't altered. And then we get these extra terms out here. You'll see that this one here is very much like your traditional Reynolds stress term. So that's all we've done. We've just Reynolds averaged the compressible full conservation Navier-Stokes equations and energy equation with a Fourier heat law built in. So if I say that the flow's incompressible in like a weak definition for that, I might say that, okay, the density change is 0, then equation 2.5 and 2.16, they'll reduce to what we had before. And that's what you see in 2.17 and 2.18. And so the first equation, right, is just nothing but the D'Alembert conservation of mass equation, and partial rho partial t went away because it's not varying in time at any spatial position. So we've seen this equation many times. And that's exactly the same. And then let's look at the next equation. Well, this is a conservation of momentum again. And I'm very thankful that that looks exactly the same as the previous one. And you'll notice here's this Reynolds stress term. So that's the exact same Reynolds stress term that we had before for incompressible flow. So they look exactly the same. So you see, it's much easier to kind of go through the motion of just using compressible equations in the first place. Okay. And I should note, well, how do we go from, say, 2.16 to 2.18? Well, obviously this term here was 0. This term here is 0, but why? Energy decouples. Right, so in the incompressible flows, we don't really need an energy equation. And this term is 0, and this term is 0. Because of the density fluctuations and averages, they're going to be pulled out and go to 0. So that's what happened when you go from 2.16 to 2.18. Okay. A few notes about this conservation of energy and momentum is that, well, first of all, the whole set of equations is underdetermined and not closed, right? That's all it means. And it does only really mean what like the net mean effects of turbulence are. Right, so we're not tracking individual quantities anymore, like we would in a DNS or LES. And of course, they're not closed, and that means they require additional relations, which is what closure is, additional equations. And we'll look at exactly what happens when we take these moments and everything. And there's a few terms. For example, one might be rho, ui, uj, prime, 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 bar, right? That's over the whole equation, not just density. And there's also these density-generated terms. I should write these here, sorry. And what would exactly, example be like rho prime prime u prime prime j. And let's see. Yep. Ui bar rho prime prime uj prime prime bar. Well, since this bar is over there, it'd be ui bar rho prime prime uj prime prime bar. Okay. Might also be mentioned that in compressible flows, these density generated terms are going to disappear, and that's what we showed in equation 217 and 218. And in compressible flow terms, you'll notice that the continuity equation has a source term. It is conserved, but what is that term? Of course, it's partial xj of rho prime prime uj prime prime bar, and that can be seen right here. And that's very strange. And it's not really something that's tractable to model or even develop in a flow. So what happened? This was recognized as sort of a major problem. And this is where the idea of mass averaging came into being, was applied. And here, I'm going to define the mass average, which is an important equation. And I do it as like an example for U. So now you'll notice that I have a tilde, and that tilde will denote a mass weighting average. That's right there on the U term. Oh, right there. And the bar will denote conventional averaging. So of course, this is just our new definition of an average velocity. Mass weighted averages. Why is it called mass weighted average? Because we have a rho bar in the denominator. So this is quite a trick, and you'll see the benefit of this trick momentarily. So the first thing is we can try and redefine and write our velocity using mass weighted averages. And we'll do that here in equation 220. So here U prime, a single prime will be a velocity fluctuation about the mass average. So see, just like before we had a time average plus a fluctuation about the time average, we now have a mass average plus a fluctuation about the weighted mass average. And you can see it's done by definition for, say, momentum, because our compressible form of Navier-Stokes involves what? The momentum term, the second term of momentum, right? Rho U. I. So that's where that comes from. So what do? Let's try and apply this technique to our full set of equations. So we're going to multiply equation, sorry about that. We're going to multiply equation 220 right here by an expression for rho, and we'll obtain equation 221. And so we have rho ui equals rho bar plus rho double prime. And so you'll note here the densities are averaged about the time. So we're going to time average densities in our equations and mass average the other terms with velocities. And also, of course, we should recover time and mass averaging as consistent across those two terms. We're going to expand, and I'll have rho bar u tilde plus rho double prime u tilde plus rho double prime u prime plus rho bar u prime. Wow. Well, it turns out that some of these terms are going to be 0 from the definition of our mass averaging in 219 right there. So that's good. And you can see this term, well, we're going to average this whole thing, sorry. Anyway, we're going to come down here, and we have this term, and then we have this term here. And of course, the averages of an average is going away, so we just don't write the bar. So now we have a definition of rho ui bar equals rho bar ui tilde plus rho ui prime tilde. Using equation 219, you can see that this first term is zippo, and or second term is 0, and we can reduce this as like this equation. Okay, so we'll need this little definition in a second, and I'd like to really illustrate two major differences between these approach. In conventional averaging, right, ui double prime is 0, right? But not so much in this case. Here we have rho ui double prime bar is not equal to 0 as mass averaging ui prime is not equal to 0 and rho ui prime not equal to 0. Okay? We can also apply the exact same technique. I'm going to move this up. You can still write for all these other equations. So we're going to do a mass or Favre averaging on static enthalpy, static temperature, total enthalpy, and you can, through the same approach, basically define all these other parameters in 2.27. Okay, so if we're going to continue here, we're going to take equation 2.6 and multiply by density from equation 220, definition of it, and we'll find this particular expression, 2.29, and why we're trying to work on the energy equation. Now we're going to mass average this whole equation like this, and it'll reduce into bars on individual terms. And there's no bar because this is essentially going to be the same term with and without. And I just noted a few properties here which came through the same approach in 228. So, and also this is an error. There should be a division sign I noted. So we can take equation 230 for the averaged mass weighted per unit volume total enthalpy and write it as 232. We might also just expand H itself as the mass average plus the fluctuation and expand out this equation here and substitute this expression for H tilde here into this equation, and we will get this new equation for fluctuation of total enthalpy. So why do we do all that? I just want to point out a few things. Well, first of all, what's useful is the equation 2.20 and through 2.30 are very convenient for experimentalists. And that's part of the reason this approach was chosen. Because if you do this mass averaging, a lot of people would argue that, well, the measurements I take in the wind tunnel aren't mass averaged. Well, it's true that in compressible flows, some of them are. And for example, some hot wire techniques will be directly compared to rho ui prime and temperature. And for supersonic speeds, if you can have a device that lasts in there, you'll be able to measure something like mass averaged enthalpy terms. The pressures are usually directly measurable, so that's not a problem. And so that's probably some of the reason these choices were made by Favre and others in the 1950s and 60s. And actually, I remember this being a point of confusion. At NASA Glenn Research Center, we were actually doing PIV measurements of high-speed turbulent jet flows. And there's a lot of arguments between the CFD people and the experimentalists if we could directly compare our Favre-averaged CFD predictions with those flows. And it turns out in some cases you can, in some cases you can't, because the experimentalists were trying to measure directly velocity, but we were obtaining from our CFD codes a mass-weighted term. And so there's always a little bit of difference in that situation with PIV. Kind of before we continue to get some of the most important equations, which would go into modeling, is to try and understand these relationships, right? So if I'm directly measuring velocities, how do I get like mass-weighted velocities and compare them? So this is where this would come in to kind of resolve some of these issues that maybe the NASA researchers faced. So we want to look for a relationship between U bar and U tilde, and we would establish that using equation 211, which is the average density equation. And this other equation, which is rho ui prime equals 0. So combining those two equations, you can write 2.35. And of course, you can also write this as negative rho double prime ui prime all over rho bar. And now I'll take the mean of 220, which is that average density equation, and I'll rearrange it, and you'll just see it's negative ui prime bar. Excuse me, that was, it's the averaged equation applied to U, not density. Okay, so I can combine these, and I will get U tilde minus U bar. So remember, that's the mass average velocity minus the mean velocity, and that would be rho prime prime ui prime all over rho bar. And I think that's a pretty neat equation because you can see now I have a tool to assess the differences between mass averages and time averages if, say, I have certain flow regimes. So at very low speeds, I would expect this difference on the left-hand side to go to 0, right? Because there's no compressibility in low Mach number flows. So just general rule of thumb, if your Mach number is less than, say, 0.2, I would expect the left-hand side to be close to 0. And as it becomes bigger and bigger and compressibility effects increase, then I would expect this difference to grow. In fact, you could say, well, my mass averaged velocity quantity would be this quantity, which I can get from CFD plus, what, ui bar. So the right-hand side should be extremely small for moderately compressible flows. And so this gives me a direct tool as one example to compare my mass-weighted CFD solvers with, say, a PIV of an experimentalist who is really directly measuring particle displacement, which they're approximating their own ways as velocity. So that's cool. And let's play around with this a little bit more to find some other interesting things. What happens if I set I equals to 1 in the above equation? And now you can see I have the differences between, and I could set I equals 2 or I equals 3 for V and W. Say if I equals 1, right, that's the U component of velocity. 2 is V, and 3 is W, just as a reminder. I can set either one, but I'll set I equals 1, because it's my choice in life. And I set that in the equation, and now you can see I can show that U tilde plus U prime goes as U bar plus U double prime. If I multiply both of these sides by density and I do my averaging over the whole equation, and you'll remember way back in the beginning when we were talking about statistical review that we can then apply the averages to each term individually, we'll get 2.40. We also note that this is 0 by definition, and rho u double prime can then be written as rho bar plus rho prime prime, u prime prime equals, and it turns out from the energy equation, E prime prime u prime prime bar. And I'll note this is the energy equation, right? And so that's an energy. Anyway, if I combine this expression with 238 right here, I'll get this equation. So what does this one mean? This is another difference between mass average and velocity average, and I'm getting this important little difference here, that within the averages that are mass average of, say, density with velocity, the fluctuations with mass averaging, which is on the left term, is going to be equivalent to Reynolds averaging. And it turns out you can establish all these same relationships for the other types of variables using almost exactly the same procedure. So one example for that is, say I wanted to establish the relationship between, say, t bar and t prime, and I wrote over this is t bar, excuse me, and this is t tilde, not prime. We can then take 228, and I'll scroll up to remind myself what it is. Okay, so this is our density enthalpy, density total enthalpy, and density temperature fluctuations. We'll expand rho as rho bar plus rho double prime, right? Reynolds averaging, and that should also go to 0 according to the same law of averages. Just to remember, t equals t tilde plus t prime. Anyway, we can substitute this in with 242 into 225, and you can write rho double prime t prime bar over rho. And we'll use all these in a second to try and simplify our set of Favre-Averaged equations. According to definition of t, we can also now expand this here and write t will go as t bar plus t double prime. So the mass and fluctuatings quantities are going to be the same. Multiply this whole equation through by density, and we'll get equation 2.45. And once again, you'll note that this equation here, or this term, is 0 because it's averaging a fluctuating term. And then we'll get rho t double prime equals rho double prime t double prime using equation 243, 245. So we'll combine them. So there's 243 right here. Combining them, we should get, if I do the math right, rho double prime t double prime bar over rho bar equals rho double prime t prime over rho bar. Okay, a few other notes. You'll see that the differences, and what's the bottom line, between the two averages depend on the density velocity correlation. Which is rho double prime ui prime bar, or rho double prime t double prime bar. Okay. Oh, I should also write two more terms, which we showed, rho double prime. Yep, t prime, that's another one. And the last one would be rho double prime ui double prime bar. Okay, so those are the four we derived or showed. Okay, well, all that's well and good, and we're going to use this in a second. And now we're going to do the Favre-Averaged definitions which we showed in equation 2.9, 2.11, 20, into our Navier-Stokes equations for continuity and momentum. So you see right here, here's rho bar plus rho double prime. So this is the continuity equation. And what do we get? Well, remember density is just your typical time average. And in the second term, you'll have your Favre-Averaged terms for rho u j, right? And we're going to apply the same mass averaging to the momentum equation. And of course, just the time averaging to the density terms for momentum. So this is your momentum term. So that's really all we've done here. And then use these averaging forms, which we just talked about. Okay. So I've made the substitution of, well, I haven't taken the averages yet, but now I want to take the averaging of these equations and then use set terms to 0, which I showed were 0 in this previous section, 2.12. And now we get the two important equations, which are the base equations for conservation of mass and momentum. And let's just make some interesting notes about these. So using mass averaging, and I look at the continuity equation compared to the original one, what are the differences? Well, the first term is now working on rho bar instead of rho, and the second term is rho bar u tilde. So that's the time average times the mass average of u. And we defined u tilde way back in the beginning of the section, right? So that's just the mass averaged of u. The good thing, and you see, is when we operate in the compressible equations, we don't have that second term in the conservation of mass equation anymore. And so by just doing mass average substitution and removing terms based on statistics that are 0, we have attained a mass average continuity equation which contains the same number of unknown terms as the original equation, which is good. Yay. Okay, so then remember when we Reynolds averaged the momentum equation, the incompressible one? What appeared? One extra term, and that appeared in this term here, and then it was moved over to the right-hand side. What was that term? That was the very definition of Reynolds stress, right? So originally it's tau ij equals negative rho ui uj bar. And I guess I need to have double primes here, right? Because it's the fluctuation about time, because it was Reynolds averaging. So compare that incompressible Rand's equation with what we have now. And it's really amazing, is you now have the exact same number of new terms in the compressible form of equation as we had in the incompressible one. So this, nobody ever saw this before Van Driest and Favre introduced it. And it was just like kind of mind-blowing because a lot of the people doing all the traditional turbulence modeling would work on incompressible flows because they didn't have to work with all these extra terms. And just by doing this little mass averaging trick, which, I don't know, it seems so simple in principle, it made just a huge impact. And 10 years later, in the 70s and 80s, people were starting to run CFD codes with the mass-weighted closures, which are their own closures. Some other notes, and in mine, I'll read it directly to you. I said comparison of the continuity equation 249 and the moment equation 250 obtained by the mass weighting approach. You can compare them with the conventional approach, and you'll see that we have the exact same number of extra terms. And so this term here, this is really a mass averaged Reynolds stress. You can see it's a single prime, meaning it's the mass averaged fluctuations, and there's no bar over rho in the traditional Reynolds average. So here's another thing you can think about. What if we took an incompressible Rand solver and we calculate the Reynolds stress, which should come out of the model if you use a Reynolds transport or a Reynolds stress transport equation, and you can compare that to the Favre-averaged ones. For low-speed flows, they should be exactly the same result. For high-speed flows, your incompressible Rand solver is totally going to fall apart because of compressibility effects, and you would expect them to be very different. you'd expect them to be. So that's another interesting tidbit to think about. The bottom line, there's two major exceptions relative to the incompressible form. There's the viscous stresses are different. Right, and that's tau ij, which we just saw. And the so-called Reynolds stresses is now defined as, say, I don't know, if you want to make it a tilde or something, just to denote it differently. That's a negative bar rho ui uj prime prime. That's the huge difference in the two. Okay, we maybe have, according to my iPad at least, we have 7 minutes left. Let's just look at the energy equation today, then we'll close up the class. Okay, so we've worked on I see some people are still writing, I'll leave it there. We've looked at the conservation of mass, a momentum equation with mass-weighted averaging. But we have a third important conservation equation, which of course is energy. And what will I do? Once again, I'm going to take my mass-weighted definitions. I'm going to substitute them in my energy equation, which I think was 2.3 in this section. And I'm going to do that for my total enthalpy. See, that's total enthalpy and static enthalpy equations. And so I haven't made a calically perfect gas assumption either. This is valid for real gases. It would also be valid for chemically reacting flow if I added in extra terms for my chemical reactions. But we're not going to do that. This isn't a combustion class. Okay. So I have two forms of my energy equations. These are the two most general forms. This is, I guess I just pull away my kinetic energy from the second form, which is fine. And there's certain reasons you might want to do that for different problems. So this is the difference between the energy formulation and the conservation of mass and momentum. We are not going to replace UI. By its average and fluctuation component when its derivatives such as partial ui, partial xj are multiplied by tau ij. And so we're going to just not do that. And we're going to take the averages of all these terms after replacement, and we'll obtain what is the two governing equations of mass averaging for energy. And that's what these are. For static, this is obviously static enthalpy, this is total enthalpy. So these are equations for the mean energy. So I think this is where we're going to pause until Monday. And on Monday, we're going to try and finish this handout and also have a new handout on boundary layer equations. And we're going to try and reduce the compressible form of these equations, which are shown in the rest of this packet, to boundary layer forms, because the boundary layer equations are usually the basis for a lot of development of turbulence models and also are going to correspond to the computer project when we get into programming boundary layer flows. Just some quick notes about these is that these are just general. And you'll note, like, if you compare them to the original energy equation compared to the incompressible one, there's way less terms. But there's interesting ones that appear, like, say, U prime, tau, ij. And just so you know, sometimes I look at this and I'm like, oh, there should be an average there, but there's no average. The average is over U tilde tau ij, but it just reduces to tau ij. Okay, with that, we'll stop here and come back Monday to finish this and look at, like Reynolds stress term. Okay? So thanks for your time.